Thank you, Monica, very kindly for the introduction, and thank you to Dara and Willem for the invitation to present today. As you just heard, I had a gardening mishap. Well, it was a gardening mishap. I tried to lift a large plant pot in the garden with my back rather than my legs, and I've spent the last 10 to 14 days lying on my back trying to recover. So if you can imagine me sort of plumped up here with cushions, struggling to give this presentation, then yeah, I'd love to be there, but it's a little bit difficult at the moment. What I'd like to talk about today is basically some work by a bunch of my current and previous PhD students. There is all about doctoral training and training the next generation of data analysts and statisticians. And so I'd really like to sort of bring in some focus of the work that these students have done. You can see their names there, taking the starring roles. The second list of names there is the supervisors who have been involved in many of the projects that I'll present. I'm going to talk about analyzing data via distributions, and I'll explain what that means in a minute. And then I'll give 5 research vignettes, so little stories about what each of these students have been working on. Just a couple of points about this talk, because I'm so excited to talk about all this work. There's so much content in this talk that it's going to be a bad talk in the sense that, when you give presentations, you're supposed to, make just a few concise points and make them well. Well, I'm going to do the opposite. I'm going to try and give you as much information as possible. Just, see if you can hold on, just because I'm very excited about all this work and just want to talk about it. The other point is that there's a difference between vignette and vinaigrette. And I guess if you don't know the difference between a research vignette and a research vinaigrette, then all I can say is that one of these is going to taste much nicer than the other, and I'll leave it up to you to decide which that is. Okay, so why might we be interested in analyzing data in distributional form? Well, some data actually arises quite naturally in distributional form. So one example here is if you're sort of thinking of air pollution data and you want to analyze sort of the levels of particulate matter, the particle sizes within air pollution data. Now, if you take a sort of a sample of gas, you then don't go through each particle in that gas sample and say, okay, how big is this particle? Okay, its diameter is 1 micrometer. And then you go to the next one. How big is this particle? Okay, well, this one is 1.1 micrometers. That would be amazingly time consuming, and that's not how the technology for recording these data work. Instead, what they do is they take a sample of the gas, they stick it in the machine filters, and then it comes back to you and says, okay, Scott, well, between 1 and 1.1 micrometers, you have 20,000 particles. Between 1.1 and 1.2 micrometers, you have 50,000 particles. And so really what you're getting there is a description of the distribution of the particle sizes, and in particular, that's in a histogram form. So if you sort of look at the cyan histogram down at the bottom here, that's exactly what we have here. At a particular time point, we have a histogram on the distribution of a bunch of particles in the atmosphere. Now, of course, this distribution changes over time, and the plot on the sort of bottom right there with the multicolored one basically shows you how this distribution is evolving over time. So there's time on the x-axis and particle diameter on the y-axis. And if you sort of look at the big red line going down there, that's a slice to a particular time point, and that corresponds to the distribution that we can sort of see on the left-hand side there. So we've got data which is distribution, it's changing over the time, and we would like to model these data. So the question is, given this, how would we analyze this kind of data? But if you're sort of evil-minded like me and you think, well, okay, suppose we can answer this question, and we can come up with these techniques for analyzing data that arise as distributions, is this not an idea that we can exploit in other ways? So for example, suppose we have a very large data set, 100 trillion observations, or some very large number. We can analyze these data, in the standard way, using maximum likelihood or Bayesian inference or whatever we want, but it might be computationally difficult. It might take a long time. But let's consider this idea of creating a distribution from these data. So, the picture on sort of the top left there might be a histogram of the data when we construct a histogram from these, 100 trillion data points. This histogram now comprises only of a few hundred numbers, but quite easily you can see where the data is, the shape, the scale, that there is 2 modes. And if, for example, we want to fit, a 2-component mixture model, it seems that, from these data, we can quite easily make a really good guess at what the parameters of this model would be. But because there's only such a small amount of data here now, they're just counts, in principle, we can really quickly fit these models to the data when they're summarized in this form, compared to if we have to sort of, iterate over, 100 trillion observations. So that's the idea. We sort of take a large data set, by summarizing it in distributional form, we reduce the size and the dimension of the data. Hopefully, we're retaining information that's important for fitting the model, like location, scale, and shape, and things like that. And then, hopefully, we'll be able to analyze the data much more quickly. So the question really is, okay, given this concept, how then might we analyze data that come in distributional form? And for most of this talk, when I say distributional form, I'm going to be focusing on histograms, but a lot of the results that we have sort of generalized to other distributional form. So the first vignette is work done by Jasleen. She's got a PhD a few years ago now, and she's currently working as a lecturer in statistics, or maybe statistics and data science at Macquarie. And part of her PhD was to answer just this basic question: how do we, we're interested in likelihood-based inference, just to sort of keep things in a sort of a particular area. How do we construct likelihood functions that allow us to model when our data have been summarized in a distribution in a histogram form? So the general approach is really quite simple. So let's suppose that we've got a likelihood function. It's a standard likelihood function, L of x given theta. This is what we would specify if we're sort of modeling any regular data. So x is our classical data, our micro data, if you like. Theta is the parameter we're interested in, and L is the likelihood function. We want to fit this and come up with estimates for theta. But we're not actually observing the data, x, or at least we're not going to look at it. Instead, what we're going to do is we're going to take x and turn it into a histogram, for example. So there's this kind of data generation process that we have. We imagine that, given some parameter value theta, under our model, which is captured through the likelihood, data x is generated. Given that data x is generated, there's some process, which I'm just going to write as f here, to create a histogram from that. And so these two terms here just correspond to the process of, under our model that we want to fit, we're generating the histogram. Now, why have I got an integration here over x? X is the data. Well, if I observe a histogram, and I put my observed histogram in here, it's not too difficult to appreciate that there are an infinite number of micro data, classical data sets that will give you the same histogram. And so if we want to say, what basically is the probability of generating a histogram that we observe? Well, we have to integrate over all these possible classical data sets that would give us this and add them up. So basically that's what's going on here. So really we have a simple generative process under our model. Given theta, we're generating some data and then obtaining a histogram from it. And then via this integration, we can then infer the parameters of the model that generates the underlying data, but while we're just observing the histogram. And this is pretty much the main idea for most of the talk. Okay, so let's sort of see how that works out. If we're sort of looking at histograms, let's suppose that we have data x1 up to xn. There, for simplicity, iid from some density, g of x given theta. We're collecting our data into a histogram, and we're going to do this just by saying, look, we've got some fixed bins, B1 up to BB, and there's a picture here. You can kind of see I've got bins from 0 to 1, 1 to 2, 2 to 3, and so on. And basically, we're just counting the number of data points that fall in those bins. And these counts are, S1 up to SB. So S1 is the number of data points that fall in bin 1, basically. And of course, these things sum to n, the number of data points. Okay, so when we're constructing our likelihood, we need to know what this f function is. And pretty much, as I described it on the previous page, we only want to consider we don't want to consider integrating over those classical data sets that match our observed histogram exactly. And so basically we say this function is a 1 if that is true, and it's 0 if it's not. And that'll achieve exactly what we want. So if we sort of construct then our sort of symbolic likelihood function, sorry for the highlighting, this bit here, I hope you can see my mouse, the product over the G densities is our classical data likelihood. We're going to have a 0, 1 indicator here for our function f. And if you just math that through a little bit, what you're going to end up with is something in this sort of this form here. What do we have? Basically, for each of these integrals here, we're integrating over a bin and finding what is the density of our model in this bin. Now, why are we doing that? Well, if we consider, x1, what contribution is X1 making to our likelihood? Well, X1 is going to fall somewhere in our histogram in the picture down here. Let's suppose it falls between 0 and 1. Okay, well, what is the probability that a data point will fall between 0 and 1 in the bin between 0 and 1? Well, if there's a density, the probability of getting an observation in some range on a density is just, we integrate the density between these 2 points, right? And that probability is the probability that we'll get a data point falling in that bin. So that's exactly what this term here is, this integral over the bin. It's the probability that we're getting an observation falling into a bin. And of course, we have many observations that fall into the same bin, and we have SB observations that fall into bin B. So our likelihood turns into a series of probabilities, which I'm just going to call P of theta here, which is the probability of a data point falling into a bin and raised to the power of the number of data points in that bin. And then we take the product over all bins. And this is pretty much the likelihood for a histogram. Okay, so let's sort of see this in practice. Let's suppose we're fitting a GEV distribution, generalized extreme value distribution. It's got 3 parameters: location, scale, and shape. It's for sort of extreme value modeling. We've created a histogram of counts, and this picture here is exactly the analysis I'm talking about now. So, here we've got 1,000 data points, and we created a histogram here with 11 bins. So what is our likelihood, or our log likelihood for the histogram? Well, it's, the sum over the bins times the number of the number in each bin times the log probability. And this term here, the G minus G, this is just the difference of 2 CDFs. And so this is the area under the density. Now, why would we think this would be a good idea in the first place? Well, I guess just going back to here and sort of making this clear, our original likelihood, which is this term here, has got n components to the likelihood. So if we have 100 trillion data points, this likelihood has 100 trillion terms in it. Whereas this likelihood here, so the one at the very end, the one based on the histogram, only has number of bins terms in it. So here I've got 11 terms in it. So you can see that, rather than 100 trillion observations in my regular likelihood, I've only in this case got 11 terms in it. So you might imagine we can evaluate this much more quickly, and we'll get sort of a speed up in computation. So that's what we're kind of hoping here. So on this plot here, we have the histogram is of the data that we've got. There's 2 curves here. The black line that density you can see there is the fitted density, just using the regular likelihood. And, it matches the data well. I don't know if you can see the distance from where you're sitting, but there's a red dashed line on the top of that. And that's the fitted density we get by optimizing the likelihood, the histogram-based likelihood with 11 terms in it. And they're pretty close. So proof by picture, which is, mostly good enough for me. This seems to be working reasonably well. Just to put a few more numbers on that, in sort of a very poor simulation study, I repeated this 1,000 times, and I looked at results for accuracy and time for the analysis. So in this top table up here, we're looking at the mean square error for each of the parameters. So the mean square error of the sort of the standard analysis is on the bottom, and these are sort of the target numbers that we're looking at there. We're saying what changes do we get as we change the number of bins? So B here is the number of bins. Do we do a histogram with 5 bins, 10 bins, 20, or 1,000? And this is the independent mean square errors for each parameter. And as you can see, if we have 5 bins, then the mean square errors are quite large compared to what we would get with a standard analysis. So that seems quite poor. But as we increase the number of bins, 10, 20, up to 1,000, you can see these mean square errors are converging to what we would get with a standard analysis. And of course, what I've not talked about is mathematically, in the limit as the number of bins goes to infinity, then we actually do recover the standard analysis. So what we have here in terms of accuracy is there's an optimum number of bins that we can choose where accuracy is good enough for our purposes. And here it might be 10 bins or it might be 20 bins. I'll probably call it on 20 there. Okay, but what do we get? What are we gaining? Okay, so here the bottom table is something about the time speed up. We have different size data sets across the top. So highlighting terrible. The top line here is the size of the data set. So n is 100 up to 100 million. The top line is what we get if we use a package for extreme value distribution fitting and the GEV, the fit GEV distribution command there to fit the model. And the numbers there represent the times that it's taken to fit these models. And as you can see, when the data sets are small, it's very, very quick to optimize the likelihood. But as the data set size increases, it increases. And in fact, as I get to 1 million observations, this function crashes. But if I hacked this and rewrote it myself, that it didn't crash, you'd imagine this is going up exponentially. Whereas if we look at the time to maximize the histogram likelihood, you can see that once we're beyond a certain data set size, we're much faster in the time it takes to maximize the likelihood. And if you break this down further, just these two things below the line here, we have to both construct the histogram from the data, and then we have to maximize the likelihood. Once we've got the histogram, maximizing the likelihood, sorry, the bottom line here is constant. It doesn't matter what the data set size, it's constant. The number of bins stays the same, whereas constructing the histogram takes a little bit of time. So overall, what you want to take away from this is, for acceptable accuracy, I mean, there's always some loss of information, but for acceptable accuracy, you can probably do much better time-wise in doing these analyses. Okay, so what I've said before, yep, so we can get arbitrarily close to the real data analysis as B, the number of bins here gets large, we can recover the standard data likelihood. So again, it's just a matter of trading off accuracy that we want for as much time gain as we can get. Let's talk for a minute just about how to get this integral, because our likelihood has lots of these integrals in it. When we're in one dimension, we want to say, under our density, which is this curve here, what's the probability that a data point falls in this bin? Well, it's just the difference of two CDFs of my model. And if that's available in closed form, that's very easy to do. If we're in two dimensions, as in the example here, well, I want to say, what's the probability of something falling in this two-dimensional bin? Well, I can do this by the inclusion-exclusion principle, just by evaluating the CDF in two dimensions now of each of the corners of this bin. And here's the formula down here. If we're doing this in D dimensions, though, you can kind of see this number is going to explode. It's going to be 2 to the D terms using the inclusion-exclusion principle if the CDF is available. So this is kind of a sort of a drawback of this method. It works, but it seems to be limited to sort of moderate or low dimensional histograms, which kind of makes sense. Okay, so Tom did his PhD a few years ago. He's seen the light and he's gone to work for industry and lots of money. But while I was doing his PhD, he took on this challenge. The likelihood for histograms works. It's feasible, but there's sort of a dimensionality problem here. We can't analyze easily data in sort of higher dimensions than, say, 2 or 3. How did Tom approach this? Well, he used ideas from composite likelihoods. So here's an example, sort of an environmental example. So we've got a lot of recording stations over Australia. There are 105 of them, and we're sort of recording temperature. And each of these locations, at every time point, we have an observation, and we want to fit a spatial extremes model. We're interested in extremes temperatures. Now, if we say, okay, this is a analysis that I want to use histograms for, say we've got too much data, well, then we can construct histograms, but the histograms are going to be 105 dimensional. And that's going to have a lot of terms when we're trying to do this closed form integral. So it's not viable. So what can we do? Now, when you fit sort of spatial models, a lot of the time, most of the information is, saying, from one location, what's the relationship between the data there and another location. So it's kind of a pairwise construction. So we can kind of say, well, rather than looking at this 105 dimensional histogram, we can look at, say, pairwise histograms, bivariate histograms. So here's the bottom image here is the data from 2 spatial locations, and these other images are just varying degrees of discretizing them. So we've got a 3 by 3 discretization there, which is useless, 5 by 5, which is not much better, 10 by 10 is kind of telling the information, 15 by 15 is pretty good. Probably we don't need to go any higher than that to capture the essence of the data. So we can say, rather than 105 dimensions, let's look at the pairwise histograms instead. These are now low dimensional, but then, we've got a lot of these. We've got 105 times 104 divided by 2. How can we fit the model with all these this bivariate information? And one answer to this is something called composite likelihoods. Now, if you're not familiar with that, composite likelihoods kind of say, okay, really I want to fit my standard likelihood function here. It's in whatever high dimensions it is. But I can't do that directly because it's computationally intractable for some reason. And in fact, that's the case for this spatial extremes model we want to fit. However, it might be that in lower dimensions, not 105, but say 2 dimensions, this model is viable. And in this particular spatial extremes model, 2 dimensions, we have a closed form likelihood, CDF and likelihood function. So if you have lots of, say, marginal events, X is 105 dimensions, but you can construct a likelihood from, say, 2 pairs of information. Well, do that. Construct the likelihood from 2 pairs of locations, and then do that for every pair of locations, and then multiply these things together. So you've constructed a likelihood that's the product of all the 2-dimensional relationships. That's not going to be the same as the regular likelihood, but as you know, as long as for each of these individual components, you can in principle estimate these parameters, theta, variously well, then by combining all the information, in principle, you might be able to estimate the parameters reasonably well. And this works fairly well. And there's the usual limit theorems, just like for regular maximum likelihood. The maximum composite likelihood estimator at some rate to do with root n will approach the true parameter value, and it's going to be normally distributed. So that's pretty much exactly the same as a standard maximum likelihood estimation. So we can sort of do this. We can say, okay, let's take all the pairwise likelihoods. For us, the pairwise likelihood is going to be a bivariate histogram likelihood, and it's going to be of this form here. Again, we've got the probabilities. We're raising the probabilities to the power. It's just that now we're doing a two-dimensional integration over the model, which is trivial to do for this model. And proof by simulation, we can sort of see this kind of work. So in sort of controlled simulation study, we've got 6 parameters on our model. They're sort of on the top here. The first 3 are spatial parameters. They're sort of covariance matrix. And the other 3 are basically the GEV parameters that we saw before. So again, we're increasing the number of bins 2 by 2 on each of the bivariate, marginal bivariate histograms. So 2 by 2 representation, 3 by 3, 15 by 15, and so on. And we can kind of see that the MLE is approaching what we would get if we just bit the bullet and did the number crunching on the full data analysis. So all of these are converging variously quickly, depending on how easy these parameters are to estimate. And you might say, look, about 10 or 15, at about 10 by 10 or 15 by 15, we're getting reasonably good results. Okay, so what do we gain on simulation speed? Terrible table, ignore this table. We're just going to look at the top quarter here, just on sort of the k equals 10 table here. All of these things here are time in seconds to maximize the likelihood. We're looking at different data set sizes, in the first column here for n. And TC, this is the time taken to maximize the standard composite likelihood. So 71 seconds for 1,000 observations, 31,000, I'm not even sure what that is in days, for 500,000 observations. TS is the time taken to maximize the histogram-based likelihood. And as you see, that's overwhelmingly smaller, which is fantastic. These other 2 columns are 2 different ways of constructing the histogram in the first place. It's not free. You have to sort of fairly take account of that. But these numbers, if we sort of add one of these columns to the TS column here, it's not going to outweigh the time component for doing the full analysis in any way. So this is fantastic. We can now do 105 dimensional histogram analyses via composite likelihoods, and it works fine. Okay, vignette 3. Now Prussia hates coding. He hates simulations, and he loves hard maths, which is great. So his main focus has been on the properties of this mathematical and statistical properties of this likelihood. What we've done, we've proposed a likelihood. We've shown we can fit the models, but all we really know is that in limiting form, mathematically we can recover the standard likelihood, but we don't really know if this is a good thing, if it's going to work generally, if it is a fluke, only worked in some simulations, or if that's actually a mathematical foundation to this and how accurate we can be. So I've just got a couple of slides on Prussia's work. It's fairly technical, and I'm just going to skim through it just to sort of give you a flavor of what it is. He took 2 steps. First is to do with the convergence properties of the symbol the histogram or the distribution construction process. And when we're talking distributions here, he did a more general setting where, yes, it's histograms, but it's also random rectangles, which is basically just a histogram with 1 bin, or other distributions where you can say, look, my data looks like a normal distribution. I'm going to fit a normal distribution, and that's my distribution I want to use for data fitting. So under some assumptions, we have a data generating process. Given a true parameter value, we've got a data generating process, and from that process, we can construct some say histograms or some distributions. And based on this, Prussia has sort of results along the following lines. So with random intervals, the random interval based on finite number of data points converges uniformly in probability to something. An interval, there's a limit interval that it converges to. Similarly, in d dimensions, we have weak convergence to a particular limit in d dimensions. So converging uniformly in probability and weak and almost surely, these are all sort of technical characterizations of the way we can mathematically describe how this convergence happens. And it's very useful to have these. Similarly for histogram, histogram aggregation is continuous in the set of distributions that admits a probability density. Slightly esoteric, but we can build on these things. And effectively, at the end, we sort of end up with statements that we can make about the type of convergence, under where we can measure that, what quantities are bounded by, what kind of things, and it's quite handy because the second stage of this is, it's okay to do all this stuff, but we actually want to know the practical side of this. We're going to take this, data that's generated from a model from which we construct a distribution. We're going to take that and stick it in a likelihood function and then do inference. And we want to know what are the properties of that final inference that we do. So the second part of it is Prof has put together a slightly more general likelihood function than the one I've been talking about so far. It covers, like I say, the histograms, random rectangles, and the more parametric distributions as well. But again, given some more not unreasonable assumptions and the ones we had previously on the conversion on the convergence of the distributions themselves, we have things like likelihoods of this form are continuous in the parameter space in the uniform norm. The likelihood's got continuous sample paths, the likelihood's equicontinuous on compact subspaces of the parameter space. And just to point out that the likelihood is continuous in its parameter, which doesn't sound very exciting, but if you sort of think we're discretizing the data, the data was previously continuous, so now we have a discretized form of that. It's not necessarily immediately obvious that that will result in a continuous likelihood. But with some mild assumptions, it does, and that's great. And so we sort of build up to sort of the results that we're looking for. The likelihood that we've been looking at with a finite data does converge to something as the data goes to infinity. It does so uniformly in probability. And this thing it converges to is effectively a point mass on the true value. So the MLE, as n goes to infinity, is going to converge to the true parameter, which is fantastic because we didn't know that before, and we were whistling in the wind and hoping that we were doing good enough. And so we basically have consistency of the likelihood. Now, Prof desperately needs to submit. He's got to do it by next week or he's in trouble. But what we would like to do next with this work is we have convergence. Do we have normality of this? I'm not sure if we have normality of this. I've got to check. It would be nice if we did. But the obvious thing now to do is look at the rates at which these things happen for different types of distribution construction. Do we want a histogram with 5 bins or 20 bins? Because we can look at the rates at which the convergence happens, and then from that optimally choose in some way the best discretization to satisfy our goals. So that would be a really quite useful study. Okay, that's all the theory I'm going to give you. You can sort of wake up on that. The fourth vignette is from Dr. Yu Yang. She graduated last year. Yu, again, was focused on likelihood-based inference, and in fact, she was primarily focusing on random rectangle distributions, which is basically a histogram with 1 bin, and I'll show you a picture of that in a second. She took the next step and said, okay, this kind of thing seems to be working, but what if we don't have those integrals available, even in 2 dimensions? What if we can't do it? And how can we still do analysis there or not? And the answer is yes, with a bit of work. So the first thing that Yu was looking at is random rectangles. So rather than here's a picture of sort of 1,000 observations, our classical data. We can put a histogram over that, 10 by 10, but 10 by 10 is going to give us 100 data points. And maybe we don't necessarily need to know the resolution in that much detail. If we did like a 1 by 1 histogram, if you like, we basically get a bounding box like the one in the middle here that contains all the data. And that's going to tell us location and scale, right? And that might be enough, depending on the model that we're fitting, that might be enough to fit the model. But what you kind of pointed out was that, hang on, rather than, summarizing all of these data just, by the minimum and maximum, a box, defined by the minimum and maximum, we can actually capture some of the dependence information in that data if we just, define our random rectangle just on some quantiles instead, and then retain some of the, micro data, the underlying data, classical data points as part of the likelihood. So the likelihood would have a term which is everything that's summarized in the box multiplied by the regular likelihood for the remaining data points. And if you think there's dependence in the data, then if we know our data points are out this corner and this corner, then you can kind of see, well, that's going to kind of allow us to capture some dependence information. So you've basically got a study here as we, as Q increases, which is basically saying, what percentage of the real data is actually being retained, and the opposite of that is being summarized. Our root mean square error, which is sort of this middle which is the middle column here, compared to the full analysis, the more real data that we use, we get closer to the real analysis, which makes sense. And of course, the trade-off is the time taken. So it's not highlighting very well. The time taken here. This column here is the time taken for the regular MCMC. This is the time taken. No, it's not. That's not true. Okay. Yeah. So yes, this is time taken for the sampler, and there's also some time taken to construct the random rectangles. And this here is the time ratio. So if we sort of take the full data analysis as a ratio of 1, then if we're only bringing in 2% of the data, then we can do our MCMC, or maximum likelihood estimation, 12 times faster by only bringing in 2% of the real data. Whereas if we bring in 33% of the real data, we can do the analysis twice as fast. Okay, so this was a nice observation, and it sort of gives you another efficiency slider that you can use for your analysis. Use primary contribution was saying, okay, well, our likelihood has this form. You know, we've got terms which are basically probabilities raised to the power s, where s is sort of a fixed known number. Typically, we've known what p is as a function of parameter value theta. It's had a particular form. Well, you know, and we've known it in closed form, so we could just bung it into the likelihood and just optimize it, and everything's okay. But the question is, what if we don't know what this is and we can't evaluate it? Maybe we don't have the CDF in closed form, for example. Well, just by, you know, the form of this integral, we can always get an unbiased estimate of p. You know, we could call this p hat. How we can get an unbiased estimate of p? Well, we can just sample uniformly over the bin, and then take the empirical average of this, and that'd be a Monte Carlo estimate of this integral. Now, it's useful if you sort of do you know, Bayesian computation, for example, if you have unbiased estimates of your likelihood. If you have an unbiased estimate of your likelihood, and then by unbiased, I mean, you know, you take the expected value of it, and you get, you know, the actual value of the likelihood. If you have this, then you can use samplers called pseudo-marginal MCMC methods. And it's just like regular MCMC, except that if you put an unbiased estimate of your likelihood into the MCMC sampler, you'll still be able to sample exactly from your target posterior distribution with no approximation. And this is really fantastic. So we're thinking here, okay, maybe we can get an unbiased estimate of our likelihood, and then we can do pseudo-marginal methods. Now, the problem is, while if we can get an unbiased estimate of this probability, which is easy, such that, you know, we take the expectation of this and we recover the true probability, it's not the case that when we raise it to a power, that the expected value of the estimated probability raised to a power is not the true value of the probability raised to the power. That's just not true at all. It's mathematically completely wrong, right? But this is what we need. To run pseudo-marginal methods, we need to come up with an estimate of p to the power s that's unbiased, so that the expected value of p to the power s is actually, sorry, p hat. So the expected value of the estimator of p to the s is p to the s. And if we can get this, then we can use pseudo-marginal methods. So that was sort of the technical question that you had to run with. I'm just going to skim over this. There was 2 methods. The first method is exact. It's going to give us exactly what we want. There's 2 steps. First of all, we write the log of the term that we're interested in working with. So, you know, s log p. We then use an estimator to estimate this thing unbiasedly. And we use something called path sampling. You can look it up. It's sort of an interesting method. That will give us an unbiased estimate of s times log of p. We can't then exponentiate that and say, this is now an unbiased estimate of my likelihood, because the expected value of, you know, exponent of an estimator is not the exponent of the true value of that estimator. So that doesn't work. But there's another trick that we can use called the Poisson estimator, which basically says if we have a lot of copies of the estimate of the log, unbiased estimate of the log of the likelihood, we can do a little jig here with probabilistic outcome and come up with an estimator here, which is an unbiased estimator of the likelihood. I'm not going to go into the details. There's math behind that. It's very interesting if you're into that kind of stuff. So the outcome is that we have an estimator. It works. We can do it, but it's actually computationally expensive. And because we're all about reducing computational expense here, that we wanted to reduce that. So we came up with an approximate method. And again, of the 2 steps here, there's 2 approximations. First of all, if we have lots of unbiased estimates of our probability here, and of course we can get unbiased estimates with 1 Monte Carlo sample, so these are cheapest chips. To get an unbiased estimate of the log of the probability, we can just take the log of our estimator, take a Taylor expansion around the true value, discard terms of above second degree and then take expectations. And then we kind of have this kind of approximation here. Turning it around so it's a function of log p, which is the thing we're interested in, we can then come up with an estimator of log p, this one here in blue, which is biased. It's biased because I've chopped off terms greater than second degree, and also because this term down here in red used to be a p, but I've had to put a p hat in there. So it's biased, but the hope, in sort of quotes, the great hope is that it's not very biased. We can then do another approximation to go from an estimator of the log of the probability, an estimator of the log of probability to an estimator of the likelihood by making some assumptions about, say, the distribution of the log of our original unbiased estimator of the probability. If that's normal, then ... with some hand waving, we can come up with a form here, which is another approximate way of coming up with the expected value of actually the likelihood itself being the likelihood. So an unbiased estimate of the likelihood. So all of this is approximate, but it's going to be super much faster than the previous approach. So you'll notice I love tables, so I'm just going to briefly sort of say what these two things are. So there's two steps. We're going to estimate the log of the likelihood unbiasedly. So basically, we've got a simple model here. Our data are, trivially Gaussian distributed in d dimensions. We're integrating over a particular bin, which is defined in d dimensions. Path sampling is the true value. So this first column here is the value that we get if we did the exact method. If we did the Taylor approximation, we're not doing too badly. We're sort of getting a little bit more out as the dimension increases, but for moderate dimensions, it's okay. But look over here, these last two columns. This is the speed in seconds taken either for maximization or evaluating the likelihood once. 300 seconds versus 3 seconds. 700 seconds versus 8 seconds. This is killer. This is like 100 times faster. So I'm not going to hang around for this. If this approximation is good enough for me, I'm not going to hang around for path sampling to work. I'm going to use this approximation. The second step is exactly the same. We're evaluating the log of the likelihood. This is just the numbers on the log scale. Again, but this column here is the Poisson estimator, the first one. And so it's the exact value. And BC here is the approximation just based on those normal distribution arguments that I didn't really talk about. And as you can see here, the approximation is very good, even in 10 dimensions. And it's going to drift away as it gets higher, but it's pretty good. And again, just in sort of this column here, the time taken is 1/3 of before. So if we sort of combine these two things together, then the approximate method is going to be in combination much faster than the true method, the exact method. So again, I know you love tables. I've got a really small example here. I've basically got two parameters. I just won't really go into detail what it is. I've got two parameters, mu and sigma, so it's a very simple model. For each of these, I'm looking at the root mean square error. And these things here, for mu, the model's in different dimensions. For the full data analysis, this is my root mean square error. The middle column is the root mean square error I get from the histogram-based, the random rectangle-based analysis, and the ratio is here. So I'm doing somewhere between 2.5 to 3 times worse in terms of root mean square error for this parameter. And in this parameter here, I'm doing somewhere between 2 and say 6 times worse. So it's a question is this acceptable? If it is, the time here, ratio of the full analysis to the distribution-based analysis, here we're 5 times faster, which doesn't sound a lot, but this data set only had, I'm not sure it's 50 or 500,000 observations there. But if you think for our analysis, this computation time here is constant, regardless of the number of data points, whereas this one's going to go up. If I just want to make this 100 times faster, I'm just going to increase the number of data points here, artificially, and just make it look arbitrarily good. So great. This is great work by you. And now we've got a good way of proceeding pretty quickly with models that we are not able to do that integral for. Final vignette is Hakim, who's somewhere in his 2nd or 3rd year. I'm not quite sure. He's looking at various things, but the thing I want to talk about today is just mixture modeling. We want to fit Gaussian mixture models using histograms, specifically here, and see if this is going to work out and if there's anything cute about that. Now, why do I think there's something cute? Well, let me just tell you this. So what is a regular mixture model? We're looking at a Gaussian mixture model. The picture here, we've got some data. It looks like, we can approximate this by a couple, 2 or 3 Gaussian components. The mixture model says, I've got some data points. Each data point comes from some mixture model. I've got various components weighted, the WJs here, and here I'm just explicitly writing Gaussian mixture components. If we were sort of doing a regular Gibbs sampler on this, convention is to say, for each data point, I'm going to introduce an indicator variable. For each xi, there's a zi, and basically this indicator variable says which of these components here the mixture component comes from, or it's likely to come from. So in that we can say, what's the distribution of xi itself comes from this j component mixture, but xi given z, well, this comes exactly from this particular component with mean mu zi and variance sigma zi. So zi is taking some values between 1 and j, effectively. And this is good because, when you put the samples together, you get lots of nice closed form conditional distributions. But within the sample, you have to do MCMC on all of these terms here. Now, that's fine. But let's suppose we have a large data set. So, I've got a Higgs data set picture in a second, that there's basically 11 million data points. So if we're fitting sort of a mixture model with 11 million data points, this means, I've got 40, 50 regular parameters in sort of my mixture components up here, but then I've got another 11 million parameters I've got to introduce to integrate over. Now, this might be efficient, it might not be, but I've got to do a loop over all of these 11 million parameters, and that's going to be slow. So, is there do we get any benefits from, summarizing our continuous data here down to something like this approximate? And the answer is yes, or I would be telling you about this. But let me just show you the cute bit. And the cute bit is, if we sort of think what we're doing with sort of the histogram, we're basically saying our xi's fall in bins, right? And once the data is in a bin, I can't distinguish one xi in that bin from any other xi in that bin. Okay. Now each xi has a zi that goes with it, which means that within one bin, I can't distinguish, which zi goes with which xi, or any sort of relationships between those zi's. They're all sort of mingled together in this bin. So for each bin, we can construct the set and say, okay, for each xi that's in a bin, let's collect together the zi's. And these zi's are the numbers, 1 to j, where j is the number of components. And there's a lot of them. Because they can only take the values 1 to j, well, we can summarize them in a vector. We can sort of say, let kappa 1 be the number of number ones we've got. Kappa 2 is the number of number twos we've got, and so on and so forth. So now with these vector of counts, we've described what is the distribution of the zi's in each bin, distribution of the indicator functions. And that's really good because it means, just like in this construction here, where we sort of said, we can sort of set, the prior for zi is that it's, a draw from a multinomial distribution with weights, given by the weights of the mixture components. We can do the same thing, but this vector, rather than a single draw, is how many points I've got draws from this multinomial distribution with these weights. So we're not modeling individual zi's, we're modeling the distribution at each point, which means that rather than having, capital N zi's to look after, we've got j counts in each bin to look after. And this number is going to be much, much, much smaller than this number. And not only that, we can update j of these in one go, just by a single update step here. So this is, cute in the sense that you get like a nice tweak on the mixture algorithm. So I'm completely running out of time. Just let me finish off here. So the rest is just pictures. So again, here's some curves. They all look the same. There's an original data generating curve here. There's the density that we get if we do regular MCMC, and there's lots of fitted densities we have using a histogram with varying bin widths. And apart from one that just is a bit blobby at the front, where we have too high discretization, this is looking really good. Similarly, in 2 dimensions, on the top, I have the data, so the continuous data and various discretizations on the top. And I appreciate this is proof by picture, but the bottom is the fitted density. And as you can see, most of these are pretty okay. I mean, we're comparing with this sort of true density down the bottom corner here. The one with the largest discretization is probably a bit blurry, but the others are not too bad. And maybe this is good enough for your purposes. I've talked about this before and sort of won't dwell on it too much, but if you sort of, this is sort of computation efficiency again. So, this is, the y-axis is log time to run the sampler or evaluate the likelihood. The x-axis is the log number of data points that we're analyzing. And this blue line that's going up scarily, exponentially, is what we get from running the classical sampler on this, using the full data set. And the flat lines here are what we get from doing a sampler based on the histograms. Now, why are these flat? They don't change. The data set can go to infinity, and we're going to get constant computation here. And that's because, remember, the likelihood, the computation is proportional to the number of bins, not the number of data points. So once we have our degree of approximation, we've got constant computational cost in regards to the data set size. Okay, I'm just going to sort of finish up with sort of a few more pictures. We went and raided a machine learning data repository. So for various data sets, we've done, what have we got? So each data set has got a number of data points. This is a small one. We've taken, we're fitting a 15-dimensional mixture distribution. We're only doing it in 2 dimensions here, just for sanity, because it's not going to scale that great. We've got various degrees of approximation on the top, and then various plots of the fitted density at the bottom. I've just realized as I'm putting this talk together, some of these densities here are on a different scale, so it looks as though it's the worst approximation, but really it's just zoomed in more. So really, if we're sort of looking at this approximation here and comparing it to sort of the true analysis here, it's not too bad. How well are we doing in time? So that these colored numbers here, the time is how long it takes to do one sampler iteration. And the other numbers are, the bottom line is how many bins or data points that we have. If it's colored in red, that means we're doing worse than the original analysis, which is bad. If it's colored in green, that means we're doing better. So here we can kind of see if we take the biggest discretization, our sampler is going to run faster, and we're going to get this degree of approximation compared to the truth. Now, this is only with 500 data points. If we go to models with larger numbers of data points, well, I guess you can see that, with more detailed discretizations, we're now starting to do better than the original sampler. And if we sort of take the limit of this and look at the Higgs data set, this is 11 million observations, then the original sampler basically takes a minute to do one iteration of the sampler, whereas depending on the discretization we want, and I acknowledge this is a simple representation of the posterior here, we can do it in 2 seconds if we go to the smallest resolution. Okay, so I've given you the same story 99 times. I hope you've got that point coming through. So let me summarize that, working with PhD students is one of the best parts of doing research at universities or research centers. The ideas and things that you come up with are fantastic. They're fun. They're very diverse. And they're very exciting to try and get working. Even though I've sort of focused a little bit on sort of the stats here, a lot of these things are motivated by wanting to do real data analyses that aren't quite possible with the methods that we have. And this is exactly what DARE is all about. So I'm going to finish up there and say thank you very much. I'm just going to finish with a final comment and no pressure on Samudra or Yi, who can finish their PhD research. So I can include this in the next version of this talk. So thank you very much.